Hi, um, welcome to the second part of our biological molecules lecture. Today we're going to discuss carbohydrates and lipids, where last time we talked about proteins. Okay, so to just get us back in the mode about biological molecules, this section introduces carbohydrates, proteins, and lipids. So we've already talked about proteins within biological molecules. And all of these are organic molecules that are really important for our cells. Biological molecules are based on the versatile element carbon. This section explains how macromolecules, which have a great diversity of function in organisms, are assembled from smaller organic molecules like glucose, amino acids, glycerol, and fatty acids. Okay. So life as we know it would not be possible without water. And we talked about this extensively in the water PowerPoint. Understanding the properties of water is really an essential part of any study of biological molecules. Carbohydrates and lipids have important roles in the provision and storage of energy, and for a variety of other functions, like providing barriers around cells. Okay, again, we're going to really get into a lot of detail and talk about the phospholipid bilayer of all cell membranes and the cellulose cell walls of plant cells. Okay, the four most common elements in living organisms are, in order of abundance, hydrogen, carbon, oxygen, and nitrogen. They account for more than 99% of the atoms found in all living things. Carbon is particularly important because carbon atoms can join together to form long chains or ring structures. They can be thought of as like the basic skeletons of organic molecules to which groups of other atoms attach. Organic molecules always contain carbon and hydrogen, and this should all be review for you from STEM. Okay, we really looked at organic chemistry and carbon pretty extensively in STEM. The term macromolecule means giant molecule, and there are three types of macromolecule in living organisms, namely polysaccharides, proteins, which are polypeptides, and nucleic acids or polynucleotides. Okay? So if you look at the building blocks of these, so monosaccharides are the building blocks of carbohydrates, amino acids are the building blocks of proteins, fatty acids and glycerols are the building blocks of lipids, and nucleotides are the building blocks of nucleic acids. So polymers, again, I'm going kind of fast through this because this should be review for all of you. So I know it's been a while since STEM, but you have learned all of this. So this is just to kind of refresh your memory. The prefix poly means many, and these molecules are polymers, meaning that they are made up of many repeating subunits that are similar or identical. So monomers are the subunits. Okay? They are joined together like beads on a string. Making such molecules is relatively simple because the same reaction is repeated many times. So we talked about this type of reaction in STEM as well as in the last lecture, the protein lecture. So I'm wondering if you remember what type of reaction this is. Natural examples of polymers are cellulose and rubber. There are also many examples of industrially produced polymers like polyester, polyethylene, PVC, and nylon. All of these are made up of carbon-based monomers, okay, monomers, little units, so carbon-based units, or monomers, and contain thousands of carbon atoms joined end to end. Okay, so all carbohydrates contain the elements carbon, hydrogen, and oxygen. The hydrate part of the name comes from the fact that hydrogen and oxygen atoms are present in a ratio of 2:1, just as they are in water. Okay? The general formula for a carbohydrate can therefore be written as C to the X, H2O to the Y. Okay? Carbohydrates are divided into three main groups, namely monosaccharides, disaccharides, and polysaccharides. The word saccharide itself refers to a sugar or a sweet substance. Again, so monosaccharide, one saccharide, disaccharides, two, polysaccharides, many saccharides. Okay? So again, a monosaccharide is a molecule consisting of a single sugar unit, and the general formula is CH2O to the N. A disaccharide is a sugar molecule consisting of two monosaccharides joined together by a glycosidic bond, and we'll talk about that in a minute. A polysaccharide is a polymer whose subunits are monosaccharides joined together by glycosidic bonds. Okay, so pretty straightforward. Monosaccharides and polysaccharides. So the monomers from which polysaccharides, proteins, and nucleic acids are made are monosaccharides, amino acids, and nucleotides, respectively. Okay, so here are all of your monomers, okay, which go through various types of bonding and reactions to create your polysaccharides, your polymers, and your other macromolecules. The main types of monosaccharides, if they're classified according to the number of carbon atoms in each molecule, are trioses, which have 3 carbons, pentoses, which have, that's supposed to say 5 carbons, and hexoses, which have 6. The names of all sugars end with ose. Okay, so common ones are glucose, fructose, galactose, etc. 2 common pentoses are ribose and deoxyribose, which should sound familiar to you because those are the sugars in DNA. Hexose. The formula for a hexose can be written as C6H12O6. This is known as a molecular formula, and you guys know about that. It is also useful to show the arrangements of the atoms, which can be done using a diagram known as the structural formula. The structural formula of glucose, which is a hexose, which is the most common monosaccharide. And remember, guys, I encourage you at any time, this is the great thing about having lectures on a video, I encourage you at any time to pause it, reread what is written, rewind it, listen to what I said again, start from the beginning. If you know, the way that I do these lectures a lot of times is I'll pause it and I'll start it over from the beginning and watch it again all the way through. And I find that I catch things a lot more the second time that I'm watching it. Okay, so one important aspect of the structure of pentoses and hexoses is that the chain of carbon atoms is long enough to close up on itself and form a stable ring structure. When glucose forms a ring, carbon atom number 1 joins to the oxygen on carbon atom number 5. The ring therefore contains oxygen, and carbon atom number 6 is not part of the ring. So if you look at if you start on the left with the glucose straight chain form with carbon atoms numbered, okay, so you have carbon 1 starting at the top and numbered all the way down to carbon 6 at the bottom. Okay, and if, again, it's more of a stable structure if it's in a ring. So then carbon 1 joins to the oxygen on carbon atom number 5. Okay, and then in the next, you see the ring contains oxygen and carbon atom number 6 is not part of the ring. Okay, so the reaction that I kept alluding to, the reaction that you guys have learned about, is a condensation reaction. It's also commonly referred to as dehydration synthesis. Okay, it's a chemical reaction in which 2 molecules combine to form a larger molecule, and in the process, they lose a small molecule. Okay, that's why it's called condensation or dehydration synthesis. Okay, they're losing a small molecule. Possible small molecules that are lost in the reaction are water, hydrogen chloride, methanol, or acetic acid. So for each condensation reaction, 2 hydroxyl groups line up alongside of each other. One combines with a hydrogen atom from the other to form a water molecule. This allows an oxygen bridge to form between the 2 molecules, holding them together and forming a disaccharide or a polysaccharide. And this bridge is called a glycosidic bond. So if you look at the diagram below, when the monomer comes together, when the simpler molecule comes together with the other simple molecule, in the case of maltose, okay, you can see that there are 2 hydrogens and an oxygen that bond together, okay? And so those form a water molecule, which leaves, and then two oxygens are then able to bond, and then that bond is called a glycosidic bond. So formation of a disaccharide from two monosaccharides by condensation. So if you see maltose is formed with two alpha glucose molecules. This can be repeated many, many times to form a polysaccharide. And if you look in this example, the glycosidic bond is formed between carbon atoms 1 and 4 of the neighboring glucose molecules. And sucrose is made from an alpha glucose and a beta fructose molecule. So if you imagine a substance, or most likely a liquid, where these glucose molecules are floating around, okay? They're swimming around and moving past each other. When they come into contact with each other, they will, a condensation reaction will occur, okay? And so that's when a hydrogen, two hydrogens and an oxygen will bond, and a water molecule is lost. And then this glycosidic bond, or an oxygen bridge, is formed. These two forms of glucose are stereoisomers because they contain the same atoms, but they differ in the arrangement of their atoms in space, okay? So this is what's important to remember. These two molecules, okay, they're two forms of glucose, and they're called isomers because they have the same atom. So they have the same number of carbons and hydrogens and oxygens, but they differ in their arrangement, okay? So isomers are molecules that have the same molecular formula, but a different structure. And stereoisomers, the bond structure is the same, but the geometrical positioning of atoms and functional groups in space differs. Okay. So looking at this beta glucose, okay, here you see again the beta glucose is rotated 180 degrees. So you can see the one on the left, let me get my pen. So here are two beta glucose molecules, and they're lined up to form a 1 to 4 link. So it's switched around because in general, like the hydroxyl group is over here, but on this side it's over here. So it's not a 1 to 1 bond, it's a 1 to 4. And so here is your water molecule that forms, creating your oxygen bridge, okay, your glycosidic bond. Okay, so that's the important part, is that one glucose molecule has to be rotated 180 degrees relative to each other. So in theory, any two hydroxyl groups can line up, and since monosaccharides have many hydroxyl groups, there are a large number of possible disaccharides. So again, these monosaccharides, or these simpler sugars, they have a lot of hydroxyl, they have a lot of OH groups, right? So they're made up of carbon, oxygen, and hydrogen, and a lot of those oxygen hydrogen are available for bonding. And so depending on where they are, and what shape they are, what the structure is, and how the bonding is, there are a lot of possible bonding pairs or disaccharides that can come out of that. And the shape of the enzyme controlling the reaction determines which hydroxyl group comes alongside each other, so whether they're moving 180 degrees or not. And only a few of the possible disaccharides are common in nature. Okay. So coming back to condensation reactions, the reverse of a condensation reaction is the addition of water, which is known as hydrolysis. This takes place during the digestion of disaccharides and polysaccharides, and then they're broken down back into monosaccharides. So you have these monomers, these simpler sugars, okay, called monosaccharides. They go through a condensation reaction where they are condensed into a polymer and water molecules are lost. But when we're digesting those sugars, they have to get broken back into their constituent parts, right? Back into their monosaccharides. And so to do that, the water is added. Okay, and that reaction is called hydrolysis. So some disaccharides, like sucrose, are not reducing sugars, so you would get a negative result from a Benedict's test. Reducing sugars are called so because they can carry out a type of chemical reaction known as reduction. Okay, and in the process of being reduced, they are oxidized. Okay, do you guys remember oil rig? In such a case, a brick red precipitate is that in the test described will tell you that a non-reducing sugar is present. If both a reducing sugar and a non-reducing sugar are present, the precipitate obtained in the test will be heavier than the one obtained in Benedict's test. If the non-reducing sugars test, the disaccharide is first broken down into its monosaccharide constituents. The chemical reaction is hydrolysis and can be brought about by hydrochloric acid. The constituent monosaccharides will be reducing sugars, and their presence can be tested for using Benedict's test after the acid has been neutralized. This is a process that you have to understand. Okay, you have to understand what a test is for a non-reducing sugar, so you have to know it's a Benedict's test, and you have to know why it works. Okay, so this is describing a solution in which a reducing sugar, which remember can be oxidized, and a non-reducing sugar are present. The precipitate obtained in the test will be heavier than the one obtained in a Benedict's test. Okay, so it's important that you know the process, how it comes about, and why it does. Okay, so looking at a non-reducing sugars test in more detail, so we know what the reducing sugars test is. For non-reducing sugars, you heat the sugar solution with hydrochloric acid. This will release free monosaccharides. Benedict's reagent needs alkaline conditions to work, so you need to neutralize the test solution by adding an alkali like sodium hydroxide. Then you add Benedict's reagent and heat as before and look for a color change. If the solution goes red, but it didn't in the first stage of the test, there is non-reducing sugar present. If there still is no color change, then there is no sugar of any kind present. Okay, polysaccharides. Polysaccharides are polymers whose subunits are monosaccharides. We talked about this. The final molecule can be several thousand monosaccharide units long, forming a macromolecule. The most important polysaccharides are starch, glycogen, and cellulose, all of which are polymers of glucose. Polysaccharides are not sugars. Since glucose is the main source of energy for cells, it is important for living organisms to store it in an appropriate form. So if glucose is accumulated in cells, it would dissolve and make the contents of the cell too concentrated. And glucose is also a pretty reactive molecule, so you don't want that. You want it stored in a different form. And these problems can be avoided by converting glucose by condensation reactions to a storage polysaccharide, which is convenient, compact, inert, unreactive, and insoluble. So the storage polysaccharide formed for plants is starch, and for animals is glycogen. Glucose can be made available again quickly by an enzyme-controlled reaction, which we also learned about in STEM. Starch, glycogen, and cellulose. Okay, so starch. So you start out with a glucose monomer, which is then through condensation reactions turned into a macromolecule, which can be stored as starch in the plant. Same with glycogen. You're starting out as monomers, which through condensation reactions turn into glycogen, which can then be stored for long term. Same as cellulose. Okay, so when you get to class, I'm going to have you read and study pages 33 through 35 and really look at how starch, glycogen, and cellulose are used and stored. Okay? Okay, dipoles. So hydrogen bonds are really very important in the structure and properties of carbohydrates and proteins, and we talked about what dipoles are and why they are created with polar substances. So electrons in a covalent bond are not shared equally between atoms, and in water, electrons spend more time around oxygen than hydrogen, therefore give oxygen a slightly negative charge, written as a delta minus, and hydrogen a slightly positive charge, and the charge itself is called a dipole. Okay, so we talked about this with our water lecture. So the oxygen atom is more electronegative, and this makes it slightly more negative. Consequently, hydrogen atoms are unable to hold the electrons near to them and become slightly more positive. And so in water, the negatively charged oxygen of one molecule is attracted to a positively charged hydrogen of another, and the attraction itself is called a hydrogen bond. And we know that it is much, much weaker than a covalent bond, but it still has a significant effect. So there you see a hydrogen bond between two water molecules. And it's between the negative and the positive dipoles. So dipoles occur in many different molecules, particularly lipids, wherever there is a OH, CO, or NH group. Hydrogen bonds can form between the groups because the negatively charged part of one group is attracted to the positive part of another. So molecules with dipoles are polar. They are attracted to water molecules because water molecules also have dipoles. Such molecules are said to be hydrophilic. Okay? Molecules which do not are nonpolar and hydrophobic. Such properties make possible the formation of cell membranes. Okay? So again, this is review for you guys. Lipids. So lipids are a very varied group of chemicals. They are all organic molecules which are insoluble in water. We talked about what insoluble means. Okay, the most familiar lipids are fats and oils. Fats are solid at room temperature and oils are liquid at room temperature. Chemically, they are very similar. True lipids are esters formed by fatty acids combining with an alcohol. So just for information, esters are chemical compounds derived from an acid in which at least one hydroxyl group is replaced by an alkyl or an alkoxy group. Okay, fatty acids are a series of acids, some of which are found in fats. They contain the acidic group COOH, known as a carboxyl group. So the larger molecules in the series have long hydrocarbon tails attached to the acid head of the molecule. And as the name suggests, the hydrocarbon tails consist of a chain of carbon atoms combined with hydrogen. The chain is often 15 or 17 carbon atoms long. So if you look, this model is an essential feature of a fatty acid. So it's a long chain, okay, of carbons and hydrogens. Or it's a long tail of hydrogen and carbons attached to an acid head, okay, which is that carboxylic group, which is a COOH. Okay, and you see that double bond between carbon and oxygen. The tails of some fatty acids have double bonds between neighboring carbons. Such fatty acids are described as unsaturated because they do not contain the maximum possible amount of hydrogen. They form an unsaturated lipids. Double bonds make fatty acids and lipids melt more easily. So most oils are unsaturated. Remember, they're liquid at room temperature. And if there is more than one double bond, the fatty acid or lipid is described as polyunsaturated. If there is only one, it is monounsaturated. Okay, so here's the structure of an unsaturated fatty acid. And you can see that double bond in the tail. Okay, and again, the reason why it's unsaturated is because it is not saturated with hydrogens. It doesn't have as many hydrogens as it could. So lipids, animal lipids are often saturated with no double bonds and occur as fats, whereas plant lipids are often unsaturated and occur as oil. So if you think about olive oil or sunflower oil or coconut oil, those things are usually liquid, and like coconut oil will condense into a solid, but at room temperature it's liquid, right? And so those are unsaturated. And then saturated fats are animal fat. So if you think of like a strip of fat on a steak, okay. Alcohols and esters. Okay, alcohols are a series of organic molecules which contain a hydroxyl group attached to a carbon atom. Glycerol is an alcohol with 3 hydroxyl groups. The reaction between an acid and an alcohol produces a chemical known as an ester. The chemical link between the acid and the alcohol is known as an ester bond or an ester linkage, okay, and this happens through condensation. Okay, so if you look at the model, I encourage you to pause the video and to really look at this model. So you have, let me get my pen. Okay, so you have your glycerol here. Okay, and so your glycerol is going to bond here with this fatty acid. Okay, and so a condensation happens, and you can see that's just perfect for a H2O molecule to come out, leaving a oxygen bridge, okay, for bonding. Okay, so what you end up with is this head here, which is alcohol. Okay, glycerol is an alcohol, and then you have three hydrocarbon tails. Okay. The most common lipids are triglycerides, and these are fats and oils. A glyceride is an ester formed by a fatty acid combining with alcohol. Glycerol has three hydroxyl groups. Each one is able to undergo a condensation reaction with a fatty acid, and that's what we were looking at here. There's three hydroxyl groups right here. Okay, and so that's just like perfect for a condensation reaction. Okay. When a triglyceride is made, the final molecule contains three fatty acid tails and three ester bonds. And that's why it's triglyceride. Okay? These tails can vary in length depending on the fatty acids that are used. They're insoluble in water, but are soluble in certain organic solvents, including ether, chloroform, and ethanol. And that's because the nonpolar nature of the hydrocarbon tails. They have no uneven distribution of electrical charge, so they're not really interested in mixing with water. So they do not mix freely with water molecules and are described as hydrophobic. Okay, again, I encourage you to pause the video or to rewind it to really study that model. That model comes out of chapter 2 in your book. Okay, roles of triglycerides. Lipids make excellent energy reserves because they are even richer in carbon. Carbon-hydrogen bonds than carbohydrates. A given mass of lipid will therefore yield much more energy on oxidation than some mass of carbohydrate, and an important advantage for a storage product. Fat is stored in a number of places in the human body, particularly just below the dermis of the skin and around the kidneys, and it's not just humans, it's in animals. Below the skin, it also acts as an insulator against loss of heat. An unusual role for lipids is as a metabolic source of water. When oxidized in respiration, they're converted to carbon dioxide and water. Okay, phospholipids. Phospholipids have the unusual property of having one end which is soluble in water. This is because one of the three fatty acid molecules is replaced by a phosphate group, which is polar, and can therefore dissolve in water. The phosphate group is hydrophilic, okay, water-loving, and makes the head of a phospholipid molecule hydrophilic, although the two remaining tails are still hydrophobic. So here you can look at the difference between a triglyceride structure with its glycerol head and its fatty acid tails, okay, versus a phospholipid, which is soluble in water, so it has two fatty acid tails. Okay, and then it's got a glycerol head with the addition of a phosphate group and a head group, which can be either of these substances in column C. So this allows the molecules to form a membrane around a cell where the hydrophile heads lie in the watery solution on the outside of the membrane, and the hydrophobic tails form a layer that is impermeable to hydrophilic substances. And the biological significance of this will become apparent when we study membrane structure. Okay, all of these fatty acid tails are all facing each other, and all of the hydrophilic heads are facing out and in. Okay, keeping water in, not being able to escape because of the hydrophobic tails in here. Okay, but still allowing this to interact with the water on the inside of the cell and the water on the outside of the cell. So that is it for carbohydrates and lipids. There was a lot of information delivered in this lecture. I highly encourage you to watch the lecture again. Okay, take notes, and really you need to start making note cards, okay, and really start studying these details. Okay, and we'll do some work in class to help you figure this out. Thanks.